Hi everybody, welcome to another video in Calculus 1, section 3.6, derivatives as rate of change. Before we continue derivative, we stop at section 3.6 to study some applications of derivatives. The most important application of derivative is it represents rate of change. So, the first one is velocity and acceleration. So, definition. Suppose that the motion of the object is a function of t, because t is the independent variable represent time. The position function, let's say, is given as a function of t. So this is the position function. Generally, motion is assumed to begin at t equal to 0. We start from t equal to 0 and going forward. We're not going back with negative time. That's the usual thing. The displacement between t equal to a to t to a plus delta t. So we go from an object from a to a plus delta t. That is called a displacement. So a position is one point in this line, and the displacement is the difference for final minus initial. That is displacement. Now we define velocity. Velocity, there will be two velocity. The first one is the average velocity, where we have the change in position or the displacement over the change in time. So if we write that, assume s is a function of t, and when we write like this, the average velocity will be the position as a plus delta t minus the position at a divided by the time between them, which is delta t. Delta t, let me just write that as well. Delta t is equal to the final time minus the initial time. Of course, remove the parentheses, a minus a cancel out, it's just delta t. So that's why instead of write like that, I write just delta t. And that is the average velocity. Now, as delta t approaches 0, the average velocity becomes the instantaneous velocity. So instantaneous velocity is just this, but we just have the limit as delta t goes to 0, and because this is exactly the derivative of the position function. So this is the instantaneous velocity. Right. To distinguish between the instantaneous velocity and average velocity we will denote by a bar on the top of it, and we call just v bar. Right. So average velocity, instantaneous velocity. Average velocity is the slope of the secant line, and this is the slope of the tangent line, if we refer back to the first section. Right, now look at some example. Assume a police station is located along a straight east-west highway. At noon, a patrol car leaves the station heading east, and position given by the function f of t. Of course, the graph is going to be here. If it goes east, it is going to be positive, and if it goes west, it's negative. So what we have is, this is the highway on east and west. The police station is located in the middle. Let's say the police station here. And the patrol car will go on the right side, and the left side, the right or left of the police station. If it go to this side, if it is on this side, it's of course on the east side it's going to be positive. If it's on this side, it is negative. On the west side, that is. Right, now describe the location of the patrol car during the first 3.5 hours of the trip. So this is the function, the position function, which t is hours afternoon. So from noon and then 3.5 hours later. So this is the position function. So what do we see? So at first it starts from the station because the position is equal to 0. Now then the position getting positive and more positive. Positive meaning is, so it will is for 1 hour and a half, and then from 1 hour and a half and 2 the position stayed the same, meaning that the car parked there for half an hour and then going west back to the station and stop at negative 20 miles, which is 20 miles from the west of the station. So we start here from the station, going east for 1 hour and a half, and then rest for half an hour, and then going back west, and finally stop at negative 20 miles west of the station. So that's what this represents. So we say from 0 to 1.5. Of course, we're talking about an hour. The car going from the station, start from the station, going east, and then 1 hour and a half to 2. The car at 80 miles east of the station, which is stationary. So the car not moving for half an hour. So stationary. At 80 miles east of the station. And then from 2 hour mark to 3.5. The region will get smaller and smaller, meaning that going west, and we'll stop 20 miles west of the station. So this going west and stop at 20 miles west of the station. So that's what we get from the graph, going like this. Next, calculate the average velocity of the car between noon and 2 p.m. So at noon, the position is here, and then 2 p.m. the position is here. So average velocity is the displacement of, we call it is between noon and 2 p.m. meaning that the position at 2 p.m. minus the position at 0 over 2 hours different, which is this, right? Right, at 2 p.m. or 2 hours later, the position is 80 miles east of the station, and at noon, position is 0 at the police station, divided by 2. So that gives us 40 and of course the unit will be mile per hour. Yeah, so 80 miles minus 0 miles over 2 hours, so miles over hour, mile per hour. Calculate average velocity of the car between 2 and 3.5. So at 2 p.m. that is 80 miles, and at 3:30 that is negative 20. So this is still average velocity. Now from 2 p.m. to 3:30 p.m. So the final position at 3:30, 3.5 minus the position at 2 over the difference 3.5 minus 2 is, but just write 3.5 minus 2. So different in position over different in time. So at 3.5 hours later, the position is negative 20 miles, and at 2 hours afternoon, there will be 80 miles over 1.5, which is 3.5 minus 2. So we have negative 100 miles over 1.5 hour. So negative 100 divided by 1.5. So that is negative 66.67. Let's round to 2 decimal places. And the unit is still mile per hour. So straightforward, right? Our average velocity different in position divided by the difference in time. Now, next, at which time the instantaneous velocity greatest as the car travels east. So this is from this part is where the car going east, and because from this part where the car going west, and 1.5 to 2, that's where this car is stationary. Right, so going is what will be the point where we have the greatest velocity? Well, we won't be able to do this because, won't be able to do this exactly because we don't have the function, we just have the graph. But the way we look at the graph, of course, this, the instantaneous velocity is equal to the slope of the tangent line, right? So, instantaneous velocity is equal to the slope of the tangent line. So we will look for where the slope of the tangent line is at the greatest. So instantaneous velocity is the same as the slope of the secant line of the position function. Slope of the line. And according to the graph, won't be able to tell, but we just find wherever the tangent line is the steepest. So look like it is about here, around this point. Yeah. So that's where we have the tangent line with the steepest or the biggest slope, and that of course will give us the biggest velocity. So this is about let's say 0.7 hour after. So estimate on from the graph we can get is that it is about, so we say at this point 0.7 at t equal to 0.7. Of course, that is 0.7 afternoon, and 0.7 times 60 minutes, because that is 42 minutes. So at t equal to 0.7, meaning that at 12:42 p.m. 42 minutes afternoon, which is 12:42 p.m. The car, approximately, we don't have the function to find that, but at that point, the slope is the greatest. Is the biggest. Meaning that instantaneous velocity is the greatest. Right. If we want to estimate the actual velocity at that point, how would we do that? So we can draw the line here, so we can estimate. Let's say about 0.5 and 20 and 1 is about, let's say, 62 and a half. So when 0.5 we are 20 miles is when we at 1 hour, we roughly about 62.5 is. So we will take the difference in the y values are different in the position function. 62.5 minus 20 divided by the difference in time, 1 minus 0.5. And we have 85 miles per hour. So at this point, the velocity is about 85 miles per hour. Because we don't have the function, so we won't be able to get exact value, but the estimate is about 85 miles per hour at this point, which is the highest, which is the greatest. Right, at what time the patrol car is at rest? Now this is easy, will be from 1 hour, 1.5 hour to 2 afternoon. So at what time the patrol car is at rest? So they will be at t equal to 1.5 to t equal to 2. 1.5 hour afternoon, meaning 1:30 p.m. to 2 p.m. Right, so that's what we have. Right, the reason we don't have any function here, just to get the idea of in relation of the graph with the slope of the tangent line and the instantaneous velocity. Just get the idea about the graph. We don't do the actual calculation yet, we just do that graphically. Right, next. So what we have up to this point is the position function f of t. Velocity is the derivative. Now we define the acceleration is the rate of change of the velocity. If the acceleration is positive, the velocity increases. If the acceleration is negative, the velocity decreases. So acceleration is defines the rate of change of velocity. So this is what we have in summary. So suppose an object moves along the line with the position is equal to that, then the velocity at time t is given by this. So velocity is equal to the first derivative. Velocity is equal to the first derivative, and the speed is equal to the magnitude of the velocity or the magnitude of the derivative. It's called the speed. Of course, the speed, because the nature of absolute values is also only greater than or equal to 0, so speed cannot be negative. And acceleration is the second derivative, because it is the rate of change of velocity. And as in this section we adjust the title, it says derivative as rate of change. So rate of change, instantaneous rate of change, is the same as derivative. So the rate of change here is the derivative. So derivative of velocity, and velocity is derivative already, so just derivative of derivative. Therefore, acceleration is second derivative. So once again, derivative of velocity, velocity is derivative of position, so we have derivative of derivative, therefore the second derivative. So velocity is the first derivative, acceleration is the second derivative, and the speed is the magnitude of the velocity. We don't have the equivalent to that in acceleration. Right. So this is a classic physics problem. When you take physics, usually you will be asked this question. Let's say we driving a car. So in the car, there will be 3 devices that change velocity. 3 devices that changes velocity. And you say, of course, the gas pedal, right? When we hit the gas pedal, we speed it up. So that's the first one, obvious. If we want to speed up, hit the gas pedal. Now, if we want to slow down, hit the brake. So the gas pedal, we speed it up, increase velocity. The brake, slow the car down, decrease velocity. So the gas pedal, the brake. And so what is the last one? Right. The last one is the steering wheel. If you turn around and go backward, of course, the velocity would be negative. Of course, I'm talking about the velocity would be negative. The speed is always greater than or equal to 0. Even though you go 20 miles east or west, the speed is still 20 miles per hour. But by assumption, if we go on east, it's going to be positive. If we go on west, it's going to be negative. Usually, that's the case. So, 3 devices that change velocity in the car: the gas pedal, the brake, and the steering wheel. Of course, changing the direction causing the change in velocity as well. Right, so those are the 3 things in the car that change velocity. Right, now, before we go any further, of course, in physics, when we study about motions, it's only the first derivative is velocity, the second derivative is acceleration, but indeed they have names for the higher derivative. So just want to show you quickly. So we have the position function, which is the function itself. The first derivative is the velocity. So the function is the position function. The first derivative is the velocity. Second derivative is acceleration. The third derivative is called the jerk. And the fourth derivative is called snap, and crackle is the fifth, and pop is the sixth derivative. So the fourth derivative is snap or bounce, and then fifth is crackle, and then the sixth derivative is pop or pounce. I don't know who named this thing, but usually in physics we only go up to a second derivative. Maybe if we have to build something like the roller coaster, then we have to worry about the third derivative as well, because that is the change. We have to make the change in acceleration will be not too much, or otherwise it might cause the damage to the people riding the roller coaster. But like I said, I just want to show you that, so you, if anybody asks, then you know those are the higher derivative. So once again, first derivative, second, third, fourth, fifth, and sixth. Usually we don't go that far, right? Now, let's look at another problem where we actually have a function, so we can find the derivative and other things. Right. Suppose a stone is thrown vertically upward. Right. One more thing in the way we write this, we do this. Suppose an object moves along a line, so we just move in a line. If we go zigzag, then we have two-dimensional motion. So in this case, we not worry about that. We worry an object that moving in a line. One direction is positive, the opposite direction is negative. Right. So suppose a stone is thrown vertically upward with initial speed of 64 feet per second from a bridge 96 feet above a river. By Newton's law of motion, the position is given by this. So we have S of t is the position. And S is equal to 0 is the level of the river, the water level. Right. Find the velocity and acceleration function. So it's easy. Velocity is the derivative of the position function. Derivative of this is negative. I'm just going to do that for now. T squared derivative is 2t. 64 derivative of t is 1, and that's what we have. So we have negative 32t plus 64. That is the velocity function. Next, we find the acceleration function. Acceleration is the second derivative of the position function, or just the derivative of the velocity function. So we take the derivative of this, it is negative 32. Now, as far as unit, what is the unit? So this is look like we have feet and then second. So velocity, so think about this. This is the velocity. Velocity is the change in s, which is the change in position over the change in time. And in this case, let me just write, as far as unit goes, velocity is equal to ds over dt. So ds over dt, the unit for the position is meter, or in this case feet. I should not write the equal sign here because that could be misleading. So that gives us feet per second. So that is velocity will be feet per second. Now acceleration. Acceleration is the second derivative of the position function, or derivative of this. So we're going to have dv over dt. dv, v is velocity. Again, I'm not going to write equal sign. V is velocity, so we have feet per second divided by second. So that gives us feet per second square. So this is the unit for acceleration. Right. By the way, the negative 32 feet per second square, that should sound familiar, right? I hope. So in physics, negative 32, so negative 32 feet per second square, or about negative 9.8 meter per second square. This is called the acceleration. This number is acceleration due to gravity. And of course, when we that, it is the acceleration will be assumed at the sea level. If we go 10 miles away from the center of the 5 miles above the sea level, acceleration will be a little bit less, because the gravity closer to the surface to the earth, it is more than when it's further away from it. But the negative 32 and the negative 9.8 is the gravity acceleration due to gravity at about the sea level. So this is acceleration due to gravity. And you say, what is the 64 feet here? The 64 feet, if you look at the problem, that is the initial velocity. And then the 96 is the initial position. Right, so that's what we have from that function. And the question is, what is the highest point above the river reached by the stone? So how do we find that? So even though the object is throwing vertically upward, but if we draw that as a function of time, time will be the horizontal axis. So if we want to draw this is a function of time, so we start from 96 feet above the river and thrown up. So it's going up, and then the gravity pull it down, hit the river at this point. So the highest point might be somewhere at that case. So how do we determine that? So the stone going like this. This is the function s of t. Now, if the stone going like that, at the top, how do we know what characteristic of the stone at the top, at the apex of the projectile, of the trajectory here? So notice that if we throw an object up, and then the gravity will pull it down, at the moment it reaches the apex, it is neither going up or going down. So at the apex, the velocity is equal to 0, because it is at the point where it is going, changing from going up to going down. So because at that point it is neither positive or positive, so that's why it is 0. So at the apex here, at the highest point, is at where velocity is equal to 0. So highest point occur when velocity equal to 0, because that where the stone neither going up or down, neither positive or negative, so it must be 0. So velocity is equal to that. And we solve for that, we get t equal to 2, right? Because that will be second. So after 2 seconds, the stone will reach the apex. So just find that. So position at t equal to 2 seconds. 2 seconds after the stone is released. So we have t equal to 2, so I put 2 store into x, and then we have negative 16 x squared plus 64 x plus 96, where x is equal to 2. So that's what we have. That 160 feet above the sea, above the river water level. So position at 2 seconds. You just write, we can just write equal to 160, but we're just going to put 2 on it first. So it is 160 feet above the river. Right. So that is the first application of derivative. Velocity is the derivative of position function. Acceleration is a second derivative of the position function. Next we go to the second one, growth models. Right. Let P is a function measure quantity, or could be population, or could be cost, revenue, or a lot of other things. So if we have any function, the average growth rate, of course, is a slope of the secant line. And then if we take delta t goes to 0, we have instantaneous growth rate, which is the derivative. So whatever the function is, in this case we could call some index or some population or whatever it is. When we take derivative of it, is the instantaneous rate, growth rate. Also the rate, the instantaneous rate is the derivative. So if we have the function take derivative, that is the instantaneous growth rate. Of course, before we have instantaneous growth rate, we have the average growth rate, which is the slope of the secant line, or the different quotient. Right, the number of worldwide internet users between 1995 to 2010 is given by this equation. So roughly that, where t measures years after 1995. Of course, that's just an approximation, and they've said it is impossible. This is the nature of population. This cannot be negative, right? So how come in 1995 we have negative, when t equal to 0 we have negative 45.8? That doesn't make sense, because at 1995, at the worst possible, it could be just have to be 0. It cannot be less than 0, because population cannot be negative, right? But this is just a model, so approximately, so it doesn't, 1995 it is about 0, a little more than that, but we have all the actual data. Those are the dots here, and the line and the curve here is best fit to those points. So of course it does not give us the actual numbers of internet users at that time, but approximately this is the best function that we can come up with. Of course, not the best function we can come up with, the best quadratic function that we can come up with that fit most of this point. Right. So pretty much we have a function, and the first one is we want to find the average growth rate. So the average growth rate is slope of the secant line, right, from 2000 to 2005. So pretty much what we have is the function is that. So we're going to say the average growth rate will be t, where t measured the years after 1995 from 2000 to 2005, meaning from t equal to 10 to t equal to 15. Right, so we have the data at 15 years later after 1995. After 1995, right? So that should be 2000 is 5 years later, and 2005 is 10 years later. Sorry. So from t equal to 5 to t equal to 10, meaning 10 years later, minus the data at 5 years later, divided by 10 minus 5. Right. Of course, that is the function. Right. The way we do this is, if you have a calculator like this, I will let 5 store into x. If I want to evaluate the function at a few more points, I can just type that and then have 3x squared plus 70.8 minus 45.8. So that is when t equal to 5. And then when we do the same thing, we let 10 store into x. And then we go up, highlight the function. And we do that, we have 962.2 minus 383.2, 10 minus 5 is 5. So pretty much we have this number, subtract that number, and then divide by 5. So about 115.8, and the unit will be 115.8 millions. Yeah, this one given in millions, millions of users a year. So from 2000 to 2005, approximately about that much million of people. I mean, the number of users increased by that much, approximately every year from 2000 to 2005. Okay. Of course, you can also type the function, hit y equal to and enter the function 3t squared and use x instead of t, plus 70.8x minus 45.8. Alright, one more thing. I use this calculator for my previous class and we do some statistics. Whenever you look at the y equal to, if that is highlight the plot like this, there will be something wrong when you hit the graph. It may be causing some problem. Yeah. So in that case, you have to turn that off. To turn that off, hit second y equal to, and you see the plot, it is on now. Hit enter and have to choose off. And then second mode, back to home screen. Right. So we have the function there. If you want the graph, of course we have to zoom in and out to have the whole graph. Yeah, this one go up to 1000, so it's not going to look like this if we're not changing the windows. Okay, if we want to change the windows, let's say it might go from 0 to like 1600 or so. Let's say 1800. And each increment, let's say 100. By the way, let's not go from 0, go from negative 100. So we have something a little below it. So that is x. Hit Windows and change the x values like that. Sorry, the x go from 0 to 16. Never mind. Okay. If you want to get back to the standard, here's zoom number 6. But still, that's not what we want. Again, Windows, X, let's go from -1 to 16 here. 16. And one, in this case, one tick for 2 years. So every 2 years, they are marked. Y, let's go from -100 to 16. Actually, make it to 12, 4, 6. That would be 8. So 1800. And one mark equivalent to 200. Right, let's see the graph. And you see very close to what we have here. But of course, we'll not find the graph. We will evaluate at 5 to 10. So if you want the values on the graph, just hit trace. And when we enter the x values, like 5, it gives us the y values. When we enter 10, we have the y values. Right. So that if we want the values from the graph. By the way, when we're done with the windows, hit zoom number 6. That go back to the standard window. Right. Now, if we just want the values of the function, hit variables, y variables, function y1 at 10. In fact, we can just do that and then minus variable, y variable, function y1. We can do like that, or if your calculator is TI-84, when you hit alpha, alpha, trace, hit alpha trace, and the bottom menu pop up, there's the y1, and we evaluate 5. Close parentheses, and and then divide by 5. So that's what we have. So the unit is millions of users a year. All right, what was the instantaneous growth rate in 2006? So the instantaneous rate, so that is the derivative. So the derivative of that function, derivative of t squared 2t plus 70.8, derivative of t is 1, derivative of constant 0. So we have 60 plus 70.8. And in 2006 meaning that will be t is equal to 11 years after 1995. And we just have 6 times 11 plus 70.8. 6 times 11 plus 70.8. Yeah, it's simple enough. I don't have to type x and then let x be something. So 136.8. Right. Next, another application of derivative, and this is in business. So associated with manufacturer process is called the cost function. So the cost function is the cost of produce X item. So X, the variable, the independent variable, is the number of items. And we have the cost function. And the cost function is the setup cost and the overhead. And so usually the fixed cost and the variable cost. It is also included unit cost, which is the variable cost. So the cost has the fixed cost and the variable cost, which is a function of X, the function of number of items. So in that case, we define the average cost is the number is the cost divided by x. Since x is the number of items, so the cost divided by number of items is the average, right? So that's simple enough. So the average, just like what we defined earlier, denoted by a bar above the dependent variable. Right. And then the average cost of producing additional item is given by this, right? Now, delta x is additional items. So the cost is produced equal to that. Now, if we take delta x goes to 0, we have the instantaneous rate of change of cost. And in business, we do not call the instantaneous rate of change. That sounds like too long for something, so we call that the marginal cost. So marginal cost is the derivative of the cost function, which is approximately cost produce one additional item after x item. Alright. So marginal meaning derivative, marginal cost derivative of the cost. So that is the definition. However, the significance of that is also estimate the one additional item after producing x item. So let's say the marginal cost is equal to, by definition of derivative, I'm going to write delta x go to 0, the cost of produce x plus delta x items minus the cost of producing x items divided by delta x. Right? This works if delta x gets smaller and smaller, approaching to 0. Now, it's certainly the case. Now, it works if delta x gets smaller and smaller to 0. It kind of works if it is equal to 1. So notice that if we let delta x equal to 1, then this no longer equal to, but because 1 is still considered the small number, right? Because we go to 0 and x is the number of items. Number of items cannot get any cannot get a fraction values. So 1 is pretty much the smallest you can get, right? You can get 2, 1, you cannot get half of the number of an item. Usually not the case. So when delta x equal to 1, even though the equation is not exactly equal to, we can say that it is at least approximately equal to when we put 1 in for delta x. If we put 1 in delta x, we have approximately equal to that. Now divide by 1, we don't need to write that, right? So we have derivative is approximately equal to c of x plus 1 minus c of x. Now what if this? C of x plus 1 is the cost of produce x plus first items. So let me write this out. C of x plus 1, this is the cost of producing x plus 1 items. Producing x plus 1 items. And c of x, this is the cost of producing x items. So what happens if we subtract these two? So let's say we have produced 100 plus 1, like 100 101 items minus the cost of produce 100 items. So this will be equal to the cost of produce the x plus first item. And this has the meaning of cost of producing one extra item after x items. Right, this is x plus first, x plus 1. That means I should write th or sd, it doesn't matter, which is meaning that it's only one item after x plus 1, after x. Right, because the math, that's how it works, like that. The cost to produce x plus first items, so that's why I highlight the s is in plurals, as opposed to this is the cost of produce the x plus first item. This is only one item, this is a bunch of items. Right, now let's look at this example. Suppose the cost of the function producing x item is given by, that is the cost function. Determine the average and the marginal cost function. So the average is the bar. So we take the derivative of this. We take the cost function divided by the number of items. All of that over x. Of course, we can split them, but that's fine. So just leave it like that. Next, this is the average cost and the marginal cost. Marginal meaning derivative. So we take the derivative of this function. Yeah, so that gives us negative 0.0020 4x plus 50. Right, so we have the functions. Now determine the average and marginal cost when x equal to 100. And what does that mean? So at x equal to 100, the average cost of 100, I'm just going to enter x into x equal to 100 and I put in the function 100 store into x, and then the function negative 0.02 x squared plus 50x plus 100. Divided by x and 49. And then put in the derivative. Negative 0.04 x plus 50 and 46. I write a little space here because the question also asks us what is the meaning of that. So first of all, 49. I assume that let's say it didn't say, but the cost, let's say $49, for example. So suppose the unit here is dollars. So for the first 100 items, average the cost of produce an item is $49 each. So this number meaning the cost of producing an item on average. So for the first 100 items, I should write that too. For the first 100 items, the cost of producing an item on average is 49. Once again, let's say the unit is dollars. So for the first 100 items, the cost is about $49 each. And when we have $46, what does that mean? That means after we produce 100, the next one is going to cost $46. So this means the cost of producing an item after 100, meaning producing the 101st item, is $46. So the first 100 on average is $49 each. We know exactly, not exactly, approximately the 101st item is about $46. The cost of producing the 101st item is about, like I said, it's not exact, it's just approximation. It's about $46. So again, that is an item after 100. The item after 100, which is the 101st. Of course, if we want to find the exact values, this is the cost function, right? So I will say, what if I have 101 item stored to X and go evaluate the actual cost and have to enter the cost function, which is this, just the cost, not the mean, the average cost. So this is the cost function. Right, that is 101. Now 100 store into X. 100 store into X. And at 100 we have that much. So this is the cost of produce 101st items minus the cost of produce 100 items. Exactly, this is the cost of produce the 101st item, which is very close to our approximation of 46. So the derivative is the approximation of the cost of produce one additional item. If we want to find the exact cost of produce that additional item, we have to do this. But those numbers should be close to each other. Right, next, determine the average and marginal cost when X equal to 900. So we do the same thing. Set X equal to 900. The average cost. So the average function like that, 900 store into X. And we did enter this function earlier, right? If your calculator did not allow us to go back, as alright though, just hit second enter until we see the function that we like, until we see the entry that we want. That's not it. This is the average cost. Which is about 32. I'm not going to write this, but for the first 900 items, on average, the cost to produce each one of them is about $32.11. Now we put in the derivative. X is still 900 though. Yeah, I'm not just going to write again because you know it's going to be the same thing. Well, instead 100, it is 900. Now it's 900. So we have X is still 900 now. 0.04 X plus 50. So this is $14. So meaning the approximation of the cost of the 901st item is about $14. Right. Of course, this is the cost. We have the marginal cost, which is the derivative, the average cost, which is divided by X. We also have the revenue, still average revenue divided by X. Derivative is the marginal revenue, and then the profit is the revenue minus the cost. So, and then we have the average profit divided by X, and marginal profit, take derivative of the profit. So marginal meaning derivative, and average meaning we divide by X, and of course the interpretation is that. Right, so we have this application of derivative. After this section, we go back to study more about derivative. But I'm going to stop this section right here. As always, thank you for watching, and see you in another video in Calculus 1.